This first question looks at hydroelectric power. In a pumped storage hydroelectric system, water is stored in a dam of depth 34 metres, and you can see lots of key information outlined on your diagram. The water leaving the upper lake descends a vertical distance of 110 metres and turns the turbine of a generator before exiting into the lower lake. Water flows out of the upper lake at a rate of 1.2 times 10 to the 5 metres cubed per minute. The density of water is 1 times 10 to the 3 kilograms per metre cubed. Estimate the specific energy of water in this storage system, giving an appropriate unit for your answer. So specific energy is energy per unit mass, and in this case your energy is gravitational potential energy, mgh, and your mass is just m. So your masses cancel, and we're just left with g times h. G is a universal constant, 9.81. Your height, because all of your water is contributing to this energy at which the which the water is exiting through your turbine, you need the average gravitational potential energy of this water, or in this case the average height, therefore. So the average height is 110 plus another 17, so 127 metres, which gives you your answer of 1,250, and then joules per kilogram as your answer to 3SF. I could actually look at all of the values and see that they're given to 2SF and give this probably more usefully as 1,300 joules per kilogram, but you would get the mark in either case. Part 2. Show that the average rate at which the gravitational potential energy of the water decreases is 2.5 gigawatts. So the rate of change of something is per second. So now I'm doing mgh over time. So g and h are the same. G is 9.81, h is 127. So I want my mass per unit time. And if I look at the information I was given, I was told that I get 1.2 times 10 to the 5 metres cubed of water per minute, and I'm told it's density as well. So I know that density is mass per unit volume, or alternatively my mass per minute will be equal to the density multiplied by the volume. So my mass per minute would therefore be my density, 1 times 10 to the 3, times my volume, 1.2 times 10 to the 5. That's per minute. To make that per second, I divide by 60. So my mass per unit time is density, 1 times 10 to the 3, times my volume per minute, 1.2 times 10 to the 5, and then I want that actually per second, so I need to divide that by 60, and I just multiply by g, 9.81, and h, the average height the water falls through, 127, to get my average rate at which potential energy decreases on my power, 2.49 times 10 to the 9 watts, which is approximately equal to 2.5 gigawatts. And it's important here that you see I'm stating my value more precisely and then rounding to what they want, because that justifies to the examiner that I definitely have done all of my maths correctly. Part 3, the storage system produces 1.8 gigawatts of electrical power, determine the overall efficiency. So your efficiency is just defined as your useful power output divided by your total power input, 1.8 divided by 2.5, which is just 0.72, and that's a nice easy 1 mark. After the upper lake is emptied, it must be refilled with water from the lower lake, and this requires energy. Suggests how the operators of this storage system can still make a profit. The IB is obsessed with this idea of pumped storage. So this is the idea that you use excess energy or energy when prices are low, so for example in the middle of the night, to pump the water back up. And effectively what you have here is an enormous water battery, in that you're just storing energy for future use by doing work on it, using that energy in the first place. And that's a fairly straightforward, I hope, although the concept of average height often trips people up, question sorted.